CERN is the home of the world's largest collider, and they are on a quest to solve the puzzles of the universe that surround our world. The latest discovery from the renowned high-energy physics laboratory at CERN has made headlines. Their Large Hadron Collider has produced something quite extraordinary that has the potential to change our understanding of the universe. This study's conclusion suggests that the very concerning results might point to the possibility of life on other planets. However, what exactly is this new finding and how incredible is it? Join us as we delve into what CERN scientists uncovered in a recent experiment with the Large Hadron Collider. CERN scientists noticed something strange with a particular kind of quark. Quarks are the important building blocks of all matter and are classified into flavors by physicists. A few of these so-called quark flavors quickly decayed and were incredibly unstable. The subject of this abnormality was the beauty quark, which has a normal lifespan corresponding to 1.5 trillionths of a second. The decay behavior of the quark was very different from the predictions made by physicists using the Standard Model. Their predictions state that a beautiful quark should decay into a set of lighter particles known as leptons, either an electron or a muon, with a 50/50th chance for each particle. According to the Standard Model, the weak force should govern the decay. However, the data obtained from the Large Hadron Collider revealed a very different picture. These quarks decayed into muons just 70% of the time compared to electrons. This was particularly noteworthy because electrons and muons are carbon copies of one another. The only difference is that the muon is 200 times heavier. However, the rate of transformation shouldn't be impacted since the beauty quarks decay through the weak force. All the forces in the Standard Model should pull on these two particles equally, and both should change the same number of times. This anomaly can only occur if a previously unknown sort of particle is involved in the process. It has led some scientists to propose that an unusual type of physics might be at work. New physics resulting from the discovery of a force-carrying particle could extend the current Standard Model and answer several open puzzles. Since there are currently few methods available for searching for particles, the Standard Model theory serves as the best guide to the behavior of the strange world of particles. An exact scientific framework known as the Standard Model explains all that we know about the important elements of the physical universe. Surprisingly, physicists are well aware that this model still needs to be finished and that many more parts need to be added to the reality puzzle. Even with this reasonably high level of accuracy, the electromagnetic, strong, and weak forces are the only three important forces the Standard Model can adequately describe. Currently, there is no description of gravity's power or an explanation for the universe's most powerful kind of matter, dark matter. In the course of recent tests, scientists discovered an abnormality in the data they were examining that did not fit the known parameters of the Standard Model. This time, however, something has attracted the attention of experts, and they understood that they needed to take a deeper look to differentiate this new occurrence. Even though it is normally common to uncover results outside of this model with the large volume of data that the LHC puts out, the researchers speculated about the possibility of a brand new force-carrying particle, Z', which they named a new basic particle, to explain this extraordinary discovery. The researchers also found that this force would interact differently with muons and electrons, even though it is most likely very weak given the lack of evidence for it thus far. However, the extent to which this force interacts with the Standard Model particles is still unknown. If new force-carrying particles were discovered, this would be the breakthrough physics has been waiting decades for. If this discovery is proven, physicists believe it may help solve long-standing puzzles about the cosmos and provide a complete picture of the Higgs boson's involvement in the creation of our world, among other long-standing concerns. According to a proposal by some scientists, this unidentified force might aid in the union of the basic forces of existence, like the Higgs boson, also known as the God particle, which has been physics' main objective for the past century. The Large Hadron Collider discovered the God particle. A major turning point in particle physics was reached in 2012 with the discovery of the Higgs boson at CERN's Large Hadron Collider. Since then, the ATLAS and CMS teams have been carefully examining the properties of this unusual particle and seeking to figure out the various ways it is created and decays into other particles. ATLAS and CMS provide the first evidence of the unusual process in which the Higgs boson decays into a Z boson, the electrically neutral carrier of the weak force, and a photon, the carrier of the electromagnetic force. At the Large Hadron Collider Physics Conference, indirect proof of the existence of particles other than those expected by the standard model of particle physics could come from this Higgs boson decay. Similar to a photon decaying into two photons, the Higgs boson decays into a boson and a photon. The Higgs boson does not decay directly into these pairs during these events, rather, the decays happen through a middle loop of inactive particles that appear and disappear and are not detectable immediately. These inactive particles may interact with the Higgs boson in ways that have not yet been identified. The Higgs boson is believed to be an elementary particle connected to the Higgs field. It is this field's quantum excitation amid others in the zoo of particles. The boson itself is like a whole new species. It lacks the quantum characteristics of both the carriers of quantum interactions, such as the weak force, electromagnetic force, and nuclear interactions, and the features of elementary matter. At the Large Hadron Collider, the two massive multifunctional experiments, ATLAS and CMS, simultaneously made the groundbreaking discovery of the Higgs boson on July 4, 2012. It was declared at CERN. At the time, the new scalar boson was observed mainly in two rare decay channels, which offered the cleanest signal. The decay was observed in a pair of photons, which involved a purely quantum virtual process, and the direct decay was observed in a pair of Z bosons, the carrier of the neutral weak interaction. The discovery of the Higgs boson at that time may have completed the standard model, but this wasn't the end of investigating this elusive particle. One of the significant discoveries made since 2012 involved confirmation of the decay of the Higgs. At the time, CERN predicted that further research on this elusive particle would be conducted during the third cycle of the LHC, especially after the high-radiance upgrade of the particle accelerator is finished in 2029. This will allow the LHC to perform more collisions, giving scientists more chances to identify unusual physics, such as phenomena not covered by the standard model. According to CERN's estimates, the accelerator will produce 15 million of these particles annually as it is updated. In comparison, the LHC produced 3 million Higgs bosons in 2017. This could play a crucial role in identifying more Higgs boson flavors beyond the standard model of particle physics. Theories predict the production of up to 5 distinct forms of Higgs bosons, which could be less common than the important Higgs boson. Strong evidence of a magnetic Higgs boson has already been presented by physicists even before the improvements. However, what exactly makes this Higgs boson so significant? In the initial moments following the universe's creation, this Higgs field was crucial. It establishes the basic characteristics of the vacuum that permeates our space-time. It is the cause of the existence of matter and interactions as we understand them, as well as the reason the mass of